Hi, Dr. Robin here. Today we're going to learn about two different sorts of ways of expressing the composition of a molecule, empirical and molecular formulas. You've already been exposed to molecular formulas, like this one, which show how many atoms of each element are in the molecule. But how do we find out what the molecular formula is? In part, we do this by first figuring out the empirical formula. We usually only use empirical formulas when determining the composition of an unknown compound. An empirical formula is the simplest numerical ratio in which the elements of that molecule combine. Please note that the empirical formula may be different from the molecular formula, but we'll talk about that later. Let's talk about how to determine the empirical formula if you're given the composition of the molecule in mass percent of each element. For starters, you need an actual mass of each element, not just a percent. The easiest way to do this calculation is to assume that you have 100 grams of the compound. Of course, you could choose any mass, but assuming 100 grams makes calculations a lot easier, as you'll see shortly. Once you have masses of each element, you will use the atomic mass to find out how many moles of that element are in your 100 grams. Now you're going to start looking for that simplest whole number ratio. Every once in a while, you luck out and end up with integers after step 2, but that's actually pretty rare. So if you don't have whole numbers, find which of your answers is the lowest and divide each number of moles by that lowest figure. If you still don't have whole numbers, you may have to multiply everything by a convenient factor that will give you whole numbers. Now, I know that the last two steps don't make a lot of sense when you talk about them in a vacuum, so let's try a couple of problems. First of all, we're going to figure out the empirical formula of some unknown hydrocarbon, a molecule that only contains carbon and hydrogen. If we assume that we have 100 grams of this compound, then 84.1% of our 100 grams, or 84.1 grams, will be carbon, and 15.9%, or 15.9 grams, will be hydrogen. This is why we like to use 100 grams. It makes the math in this step very easy. Now we're going to take the masses that we just got and divide each of them by the atomic mass of the corresponding element. We take our 84.1 grams of carbon and divide by 12.011 grams of carbon per mole, and that gives us 7 moles of carbon. Next, we take our 15.9 grams of hydrogen and divide by 1.008 grams of hydrogen per mole, and we get 15.77 moles of hydrogen. Well, we got a nice round number of moles for carbon, but not for hydrogen. So we're going to take the lowest of these two numbers, which is 7, and divide both of these numbers by that. That gives us 1 mole of carbon and 2.25 moles of hydrogen. We still don't have whole numbers for both, but you can see that we basically have 2 and 1/4 moles of hydrogen. So if we multiplied both numbers by 4, that would give us whole numbers for everything. Always remember when working with these numbers of moles that whatever operation you do to one, you have to do to all of the rest of them, or else you don't maintain the same ratio. So what does this give us? It gives 4 moles of carbon and 9 moles of hydrogen. So our empirical formula of this molecule would be C4H9. Let's do another example. This time we'll analyze ascorbic acid, more commonly known as vitamin C. This is made up of 40.92% carbon. So if we assume 100 grams of vitamin C, we'll have 40.92 grams of carbon, we'll have 4.58 grams of hydrogen, and 54.5 grams of oxygen. Now let's use the molar masses of each element to convert the masses into numbers of moles. For carbon, which has a molar mass of 12.011 grams per mole, we end up with 3.41 moles. Hydrogen has a molar mass of 1.008 grams per mole, so we get 4.5 moles of hydrogen. And oxygen has a molar mass of 15.999 grams per mole, so we have 3.41 moles of that. This time we have absolutely no whole numbers, so we're going to divide by the lowest number, which here is 3.41. What does that do for our mole ratios? Well, carbon and oxygen are both going to end up with 1 mole each, since they both started with 3.41 and we divided by 3.41, and hydrogen will end up with 1.33 moles. So once again, we have some whole numbers, but not all. Is there a factor we can multiply by to change that? Well, that 0.33 looks like 1/3 to me, so let's multiply everything by 3. That gives us 3 moles each of carbon and oxygen, and then 4 moles of hydrogen. So our empirical formula here will end up being C3H4O3. Most of what we're going to look at for empirical formulas in real life will be some sort of hydrocarbon. But just for fun, let's do a problem with a non-hydrocarbon, ferrocene. Again, assuming we have 100 grams, we'll have 5.42 grams of hydrogen, 64.56 grams of carbon, and 30.02 grams of iron. Now let's use our molar masses. The mass of hydrogen should be familiar to you by now. That will give us 5.38 moles of hydrogen. The mass of carbon will also be familiar, and we also have 5.38 moles of carbon. But we will have to look up the mass of iron. That's 55.847 grams per mole. We use this to calculate that we have 0.538 moles of iron. Now at this point, if you're good at math, you can see where this is going, but let's just keep following our steps as usual. We divide by the smallest number, 0.538, and that gives us 1 mole of iron and 10 moles each of carbon and hydrogen. So our empirical formula here is C10H10Fe. So we've just learned to calculate empirical formulas. I told you earlier that empirical formulas may be different from molecular formulas. So what's the difference? Well, an empirical formula is the simplest ratio of elements of that molecule, whereas a molecular formula tells us the actual number of atoms of each element found in the molecule. A good example of this is hydrogen peroxide, H2O2. This is the molecular formula. A hydrogen peroxide molecule actually has 2 hydrogens and 2 oxygens. So you could say that the H2O ratio is 2 to 2. But that isn't the simplest ratio we could make with those numbers. If we divided both sides by 2, we could say that there's a 1-to-1 H2O ratio. In other words, for every hydrogen in the molecule, there's exactly 1 oxygen. That gives us an empirical formula of HO. In other words, 1 hydrogen for every oxygen. Again, same basic ratio that we see in the molecular formula, but this time simplified to the smallest whole number. So how do you figure out what the molecular formula is if you know the empirical formula? By using the molecular mass. Up until now, we've only calculated the molecular mass from a theoretical point of view, but you can determine it experimentally through a number of different ways. Let's look at how you can determine the molecular formula. The first step is to find the mass of the empirical formula. It wouldn't be right to call it the molecular mass, since the empirical formula doesn't always represent a molecule. The technical term here is formula weight, but you follow the same process as you would for calculating a molecular mass. Next, take the experimentally determined molecular mass and divide it by that formula weight of the empirical formula. This should give you a whole number. Finally, multiply the empirical formula by whatever factor you got in step 2. It may seem weird to multiply a chemical formula by a number, but basically if the factor is 2, it means that there are twice as many atoms of each element in the molecule as there are in the molecular formula. Let's look at an example. We're going to figure out the molecular formula of ribose, which has an empirical formula of CH₂O. First, we have to find out the mass of the empirical formula. Now, when I do this, I could write the masses out to 3 decimal places, but if you look at the molecular mass we're given, it's only approximate. So I'm just going to estimate the molar masses of each element here. Carbon is about 12, each of our 2 hydrogens is basically 1, and our oxygen is approximately 16. Add up those masses and you see that the formula weight of the empirical formula is about 30 grams per mole. Now let's move on to step 2, which tells us to divide the molecular mass, in this case 150, by the formula weight, 30. That gives us a factor of 5. Finally, we're going to multiply our empirical formula of CH₂O by that factor of 5. The empirical formula had 1 carbon, so the molecular formula will have 5 carbons. The empirical formula had 2 hydrogens, so the molecular formula will have 2 times 5 or 10 hydrogens. And the empirical formula had 1 oxygen, so the molecular formula should have 5. That means our molecular formula will be C5H10O5. Let's look at another example in which we're asked to find a formula for dimethylhydrazine. This time, we aren't given the empirical formula. We're given mass percents for each element and the molecular mass. So we're going to have to use all the tools we've learned in this video. Given the percentages, and assuming we have 100 grams of dimethylhydrazine, we should have 39.9 grams of carbon, 13.4 grams of hydrogen, and 46.6 grams of nitrogen. Using the molar mass of carbon, we see that this equates to 3.32 moles of carbon. Likewise, we can calculate that there are 13.29 moles of hydrogen in our 100-gram sample. Finally, we use the molar mass of nitrogen, 14.007 grams per mole, to calculate that we have 3.32 moles of nitrogen. We don't have any even numbers here, so we're going to divide by the smallest number, 3.32. This gives us 1 mole of carbon, 4 moles of hydrogen, and 1 mole of nitrogen, an empirical formula of CH₄N. That's our empirical formula. Now we're going to use that empirical formula and the molecular mass to determine the molecular formula. Let's start by finding the formula weight of the empirical formula. Carbon has a mass of approximately 12. Each of our 4 hydrogens have a mass of about 1, and our nitrogen has a mass of about 14. Add that up to get a formula weight of 30. Now let's divide our molecular mass of 60 by the formula weight of 30 to give 2. We therefore have to multiply our empirical formula by a factor of 2. Twice as many carbons gives us C2, twice as many hydrogens give us H8, and twice as many nitrogens give us N2. So there's our molecular formula, C2H8N2. So a couple of questions that come up when I'm teaching this. First of all, people ask, are you always going to end up with even numbers of atoms? Well, remember that even though these are theoretical numbers, they're based on real molecules, and therefore, yes, you will always get a whole number of atoms. The same thing is true when you're talking about the molecular formula from the empirical formula. You will always get a whole number factor because, again, you're talking about real, actual molecules, and you can't have fractional molecules. So importantly, because the elemental composition of a molecule given in mass percent is something we can determine experimentally, because we can also figure out the molecular mass of a compound in the lab, these calculations that we've just learned to do can be super useful in figuring out what an unknown compound is actually made of in terms of not just which elements, but also the ratios of those elements within the molecule. I hope this was helpful, and I look forward to seeing you again soon.